Okay. Hi. So we stopped at Krebs cycle. Okay. So let's okay, let's okay, so we stopped at Krebs cycle. So let's go through the acronym for Krebs cycle, which we already did in class. But for a more complete picture, I'll just go through again. Acronym. So our acronym for Krebs cycle is can I keep selling shoes for my oppa? Okay, so let's highlight the first letters. Can I keep selling shoes for my oppa? Okay, so this is the acronym you use to help you remember the substrates in your Krebs cycle. Okay, so now let us write the substrates. So C will be citrate. Then I is isocitrate. K is alpha ketoglutarate. The first S is succinyl-CoA. Then we have succinate. Can I keep selling shoes for? So 4 is fumarate. My oppa, my is malate. Oppa is oxaloacetate. Okay, so let's rearrange this so that it looks more like a cycle. Alright, now we'll join the arrows. Okay, so we stopped at this. And I told you all that oxaloacetate is a 4-carbon compound, citrate is a 6-carbon compound. Then I asked you all, how do we go from a 4-carbon compound to a 6-carbon compound? We need to add a 2-carbon compound, right? Or we need to add 2 carbon atoms. So in order to do that, we add our acetyl-CoA here. Okay, so your acetyl-CoA from your link reaction enters the Krebs cycle over here. So remember that it's between oxaloacetate and citrate. Because acetyl-CoA is a 2-carbon compound, your oxaloacetate is a 4-carbon compound, and your citrate is a 6-carbon compound. Okay, so 4 plus 2 equals to 6. Okay, then we move on to isocitrate. So isocitrate is also a 6-carbon compound. So between citrate to isocitrate, this reaction is actually just isomerization. Okay, then between isocitrate to alpha ketoglutarate is actually a 5-carbon compound. So now we are going from a 6-carbon compound to a 5-carbon compound. To do that, we'll need to remove 1 carbon atom. And for that to happen, 1 carbon dioxide molecule is released. So remember I mentioned that the decarboxylation, so when carbon dioxide leaves the reaction, is always coupled with another reaction, right? So what is this reaction? This reaction is the reduction of NAD to NADH. Okay, so this whole reaction is called oxidative decarboxylation. In which your isocitrate is oxidized and is also decarboxylated. And your reduction of NAD to NADH will allow for the oxidation of isocitrate. Okay, so now we move on to alpha ketoglutarate and succinyl-CoA. So succinyl-CoA is actually a 4-carbon compound. So from alpha ketoglutarate to succinyl-CoA, just now I mentioned that from isocitrate to alpha ketoglutarate, we lose 1 carbon atom, right, in the form of carbon dioxide. So here we have a 5-carbon atom, a 5-carbon compound, and a 4-carbon compound. So to go from a 5-carbon compound to a 4-carbon compound, what do? We decarboxylate again. And again, your decarboxylation reaction is coupled with your reduction of NAD, which is therefore the oxidation of your alpha ketoglutarate. So we have another round of oxidative decarboxylation. Okay, then from succinyl-CoA to succinate, this is where the interesting thing happens. Okay, both of them are 4-carbon compounds, so there is no loss of carbon dioxide here. But what happens here is that substrate level phosphorylation happens. So ADP is converted to ATP. So remember I mentioned in class that it's called substrate level phosphorylation because ATP is formed through the direct enzymatic action. Okay, now we move from succinate to fumarate. Fumarate is also a 4-carbon compound, so there is no loss of carbon dioxide here. Instead, we have FAD being reduced to FADH2. So maybe a way to help you all remember would be that FAD to FADH2, right, happens near the fumarate, so it's all F. Okay. But you need to remember that it's between succinate and fumarate. Okay, so I repeat, the reduction of FAD to FADH2 occurs between succinate and fumarate. Okay, so over here, the oxidation reaction occurs, or dehydrogenation of succinate. Okay, then between malate and oxaloacetate, so malate is also a 4-carbon compound. Between malate and oxaloacetate, we have another oxidation reaction. Okay, so we have NAD being reduced to NADH. So over here we have another oxidation reaction or dehydrogenation. Okay, and you have your whole Krebs cycle. So you must remember the different substrates that are involved, and you already have your acronym to help you all remember. And then you need to remember, when does the oxidative decarboxylation occur? When does substrate level phosphorylation occur? Between which molecules? And where does the dehydrogenation occur, in which FADH2 and FAD are involved? And when does the other dehydrogenation reaction occur, where NAD is reduced to NADH? Okay, so take note that this is for one turn of the Krebs cycle. So this is one turn of the Krebs cycle. But remember that one glucose molecule, so one glucose molecule, remember during the lysis reaction of glycolysis, your glucose molecule was split into two 3-carbon compounds, one of which is glyceraldehyde 3-phosphate. Then it eventually becomes your pyruvate. Then your pyruvate becomes acetyl-CoA. Therefore, one glucose molecule gives you 2 molecules of pyruvate and then 2 molecules of acetyl-CoA. Therefore, you need to account for 2 turns of the Krebs cycle. Okay, so why is this important? Because now we need to tally the NADH, basically the coenzymes and the carbon dioxide that is involved in this reaction. Okay, so for one turn of the Krebs cycle, what do we have? We have two carbon dioxide molecules that are formed. Okay, so 2CO2. Then what else do we have? We have three molecules, one, two, three. Three molecules of NADH. So 3 NADH. And then one molecule of FADH2. Okay, so 1 FADH2. But remember that 2 turns of the Krebs cycle occurs. Therefore, we need to multiply by 2. Okay, so this whole thing times 2 will give you 4 carbon dioxide, 6 NADH, and 2 FADH2. Oh, and we're missing something, okay? We are missing our ATP, most important thing. Okay, so we also need to account for ATP. Therefore, for 1 turn, 1 ATP is produced, and then if I extend this line, I'll get 2 ATP. So this is for 2 turns of the Krebs cycle. And why we have 2 turns is because one glucose molecule will lyse to form 2 pyruvate molecules during glycolysis. Your 2 pyruvate molecules will form 2 acetyl-CoA molecules, and therefore each acetyl-CoA goes into the Krebs cycle 1 time. So we have 2 turns of the Krebs cycle. Okay, so this is our tally for the Krebs cycle, and we're done with the Krebs cycle.